So this is my area. So how many field lines are flowing, passing through this area of cross section? That field lines only we will calculate. So if this is my electric field, so around the electric field, magnetic field is also producing as a free fund, right? So if there is an electric field, there will be magnetic field. Fine. So if the how many electric fields are passing through this area, if number of more field lines will be there, so my flux will also increases. If because my flux is directly proportional to my electric field, or we can say flux is directly proportional to my magnetic field, flux is directly proportional to area, and in case of magnetic flux also flux is directly proportional to area. Because of that reason, phi is equals to BA cos theta, or in case of magnetic flux, in case of electric flux, we are writing EA cos theta. We have studied each and everything. Right? Correct? Okay, fine. Now, on this principle, our Faraday's two scientists were there. One was my Faraday and one was my Lenz. Okay, Nandini, if you have any doubt, please ask me. Though I have completed your first chapter, so I don't think so that you have a problem issues in the flux. Right, Nandini?
Yes, ma'am.
Yeah, fine. Now write the heading Faraday's experimental observation. See, if Faraday has experimented so many things, in the first situation he said that if we fix the area is my fixed. We are just changing my magnetic field, increasing or decreasing. Magnetic field is changing. So what will happen? If magnetic field is increases or decreases with respect to time, then for the current inside the coil will also changes. Correct? Correct or not? The current, if this is my magnetic field line, this is inward, okay? If this is my coil, so if suppose I am saying the current is flowing in this direction, if the field lines increases, the current is also increasing. If field line decreases, the current is also decreasing because we have fixed the area. So flux is also changing. Flux is changing, na beta? Right or wrong?
Yes, ma'am.
Right? Janisha? Any doubt, beta?
No, ma'am.
Very good. Now, second theorem, second thought. If radius of the coil changes, I have put it B as my constant. Then also the current is changing. Why? Because E flux is directly proportional to my area also. If area is small, field lines is small, field lines is small, electric field will be small. Area is big, radius is big, then area will be big. Number of field lines will passes through that body or through that coil. So current will also increase. Correct? Correct? Now third. If B and A both are what my constant, coil is rotating. Because my B value is what? Flux is equals to BA cos theta. So cos theta is what? Changing the position of my coil. right? The angle between the magnetic field or the electric field with my area, vector area. Now you can say area vector. So my A and B are constant, but the coil is rotating. If the coil is makes 90 degree, that is my cos theta is 90 degree. That means my magnetic field line is perpendicular to my area. This is my magnetic field line, and I put it like this, perpendicular. Then my flux will be what? Almost zero. Correct? But if it is along, this is my area vector and this is my electric field also, or magnetic field is also like this, then it will be what? Maximum. Then also the flux is changing. Correct or wrong?
Yes, ma'am.
Correct?
Yes.
So these are the three things are there which helps to increase or decrease my flux. Maybe it is a magnetic flux, maybe it is my electrical. Clear? Now, here from the chapter you have seen that it is written what? Electromagnetic induction. That is the name of the lesson. Right? So here we will study about my EMI. What is EMI? Before that, we have already studied. If potential is changing, my current is also changing. Any doubt? If my battery potential changes, if it is 100 watt, 100 volt of battery is there, then my current will be moved. If it is 10 volt of battery, current will be less as compared to my 100. Right? So if the potential changes, the current is also changes. So here my induced current is all because of magnetic field lines, changing of area, or my rotation of my coil with respect to area and my magnetic field. These are the three factors which are induced, which is in the helps in changing of my induced current. There is none of the other factor is there. Is there any factor? Okay. So in short, our Faraday sir says that, okay, if these three factors are helpful to induce the current, then magnetic flux is also what might changing. So if current is there, beta, then there must be potential also now. Because we know potential is changing, the current will also change. If the current will change, potential will change. So here, if my induced current is changing, just think about it. If potential is directly proportional to my current, right? Current changing, potential changing, potential changing, current changing. So here, if my induced current is there, so there must be potential difference. Otherwise, how electron will flow from the higher potential to the lower potential? How the current will flow if there will no be the potential difference? There might be some potential difference. No? Then and only then the current is also moving. Correct? Correct
Yes,
or not?
ma'am.
Janisha, any doubt? Janisha?
No, ma'am.
No ना? अगर ना समझ में आए तो फिर से बता देना. ठीक है बेटा? तो मैं फिर से बता दूंगी.
Okay, ma'am.
और unmute रहे. Okay? So what I said that if the current is changing, the potential is also changing. Now here, what do you mean by the word bhari bharkam word, so heavy word? EMF and EMI. What is it?
Electromagnetic force.
And EMI?
Force. Electromagnetic induction.
Electromagnetic induction.
Okay. And EMF?
Electromagnetic force.
Yes.
So what does it mean?
EMI is the induced current, or it's produced by changing of current, and EMF is produced by changing of force.
Type of force here it is. Which type of force it is?
A magnetic force.
It is nothing, just a potential difference, dear. Current is producing, so EMI, current is what? My electromagnetic induction, right? That is what my current. Okay, so if these three things are changing, what? My magnetic field area and my changing of my coil. If coil is rotating, right? So if any of the three factors affects to flow of current, maybe it is increasing or decreasing, that current is what? My EMI. And who is responsible for the change of EMI? That is my potential difference. That is what my EMF. Nothing else. Understood or not? Potential difference changes, then my current is also changing. Now, here we are talking about induced current. This is not the direct current. Here we are not connecting it with our battery. That is my external battery. Here the current is producing because of the change of these three conditions. That is my magnetic field, my area, and my cos theta. Right? So because of the changes of these three things, my current is inducing in the coil. My current is producing in the coil. Inducing means what? Producing in the coil. Correct? So the potential difference here, if the current is changing, it means my induced current is changing. Induced current means what? My EMI. If my EMI is changing, then my potential is also changing, which is known as what? My EMF. How much force our electron we are giving to the electron so that it can move from the higher potential towards the lower potential. And then proton will move from the higher potential towards the lower potential. It means my conventional current is flowing. Is this clear? What is EMF and EMI? Any doubt? Anyone? Ask me. Janisha? Nandini?
No, ma'am.
Nandini?
Ma'am, what is EMF?
EMF is just the potential difference, beta. I have not taught you the second lesson, that's why. Potential difference, that is the difference generated in the battery towards the positive and the negative terminal. So because of that difference, my current is flowing. That is my electron is flowing. Then my proton, that is my conventional current is flowing. Understood? In the circuit.
Yes, ma'am.
That is my EMF. Okay. Now, write it down. Faraday's two laws. Faraday laws. Write it down. Faraday's two laws. Number one, law of EMI. Law of EMI. Electromagnetic induction. Who wants to write in Hindi? No? Because I have written in the Hindi. That's why. Okay. No one? Fine. I have to translate it then. मैग्नेटिक फील्ड होने की वजह से कंडक्टर में इंड्यूस्ड करंट इंड्यूस्ड हुआ, उसे कहते हैं इलेक्ट्रोमैग्नेटिक इंडक्शन. ओके फाइन. because of the magnetic field lines in the conductor, the current is induced in it. The current is induced inside the conductor. The current is induced inside the conductor, which is known as electromagnetic induction. Which is known as electromagnetic induction. Law. Next point, law. Whenever there is a change in magnetic flux, Whenever there is a change in magnetic flux linked within the conductor, an EMF is induced in the conductor. An EMF is induced in the conductor. Full stop. If the conductor forms closed loop, if the conductor forms a closed coil, this is very important. It should be closed. Otherwise, the
Ma'am?
circuit, yes, bolo, say beta.
Whenever there is change linked with a conductor and EMF is in this.
An EMF is induced in the conductor. An EMF is induced in the conductor. Full stop. Next point. If the conductor forms a closed coil, see here also we have just closed the coil. The coil should be closed. It shouldn't be open. Otherwise, the circuit will not be complete. Circuit will complete only when it is closed. Okay. So it is very important. It should be closed. If the conductor forms a closed coil and induced current will flow through it. Will flow through it. Note. In the next point, write the note. In an open conductor, EMF will induced. EMF will induced, but the current will not flow. Because for the flow of the current, circuit should be closed. The circuit should be closed. Okay. Now, next point. The potential difference, no, or either you can say the EMF, just write it down in the bracket, the potential difference. EMF is what? Nothing as a potential difference. Okay. The EMF induced because of the magnetic field lines, that is known as what? By induced EMF. That is known as induced EMF. And the current which is induced means generate. Okay. The current which is induced, that is known as what? My induced current. Written, everyone? Janisha?
Yes, ma'am.
Nandini?
Yes, ma'am.
Fine. Suppose this is my coil. I'm teaching you for my NCRT. This is my magnetic bar magnet, north, south. Who will tell me what will be the direction of current if my magnet goes here?
South.
Tanisha, Himang, and Rishi, you have studied already. Tell me.
Direction of current where?
In the
In
coil.
the coil.
Okay, outside the coil, I will ask you.
From
The
right to
quality.
left.
A to B or B to A?
A to B.
A to B.
Have you done it?
It will be anti-clockwise, ma'am, for outside.
A to B is clockwise, na?
A to B is anti-clockwise.
Anti-clockwise, ma'am.
Clock तो ऐसे चलता है.
हाँ
Clock is
मैम
moving like this.
हाँ मैम तो मैम कह रहे A to B.
तो A से निकले B में गए. तो this is a clockwise.
अच्छा मैम आपने ऐसे किया.
We went through the
Ma'am,
loop.
we went through the loop. Yeah.
अरे
Ma'am,
तो through.
loop के through गए.
ऐसे गए. ऐसे गए.
जी मैम. जी मैम.
It will be B to A ना. B to B. अच्छा तो वो loop के ऊपर से गए. Okay, fine. Fine. I understood. You're thinking I understood. Okay. And here will be not. Here I have done it wrong. Here instead of galvanometer, I have put it here AC. Yeah. The current, the galvanometer will show the. Right. Galvanometer will show deflection like this, right? Means the current will flow like this. Galvanometer deflection will be like this. Why it is like this? Because our Fleming's right hand rule. If this is my motion, magnetic field will be inside and downward will be my current. So here B side will be what? Downward. Because my motion is here. My north pole is going like this. Magnetic field will be go like this. And then B to C. If I'm writing it here, C. So the current will flow downward. Is this clear, Nandini? Because these things you have not studied it. That's the reason it is what my downward. Kanisha, understood na beta?
Yes, ma'am.
Very good. Now, if my motion, so here my magnetic flux is increasing or decreasing?
It is
Increasing.
increasing.
Correct. It is increasing because the current is producing. Now, if I take it outside, the current will reduce. Because the motion is here, just think about it. It is like this. Just turn it out. If my motion is here, my current will be downward. You can see my current will be downward. My magnetic field will be outward. See? अब मेरा हाथ टूट जाएगा ज़्यादा तुम लोग को दिखाते दिखाते. ठीक है? Now, if my motion is this side, my current will be just reverse. It will be like this. Correct? It will be like this. And magnetic will be what? Outward. So the flux is decreased. So if flux will decrease, the current induced will be what? Decreases. So my EMF is also decreases. Is this clear? Understood?
Ma'am,
So this, yeah, say beta, say.
once again repeat, ma'am. I can't understand.
Okay, fine. For that, Nandini, just go through class 10, the chapter magnetism. There it is written in. We have studied in class 10 also. Because I'm not taking your class of this one in class 12. So just go through the chapter, the magnetism lesson of class 10. There it is written Fleming's right hand rule. Fleming's right hand rule says that if this is my velocity, this one will be a magnetic field. This one will be my current. So if my velocity is going this word, magnetic field will go this inside. My current will go what? Downward. That is written. That is B to C. But if I change the direction of the magnet, it means my magnet is this way. My magnet is moving here. My magnetic field will be what? Outward. My current will be where? Downward, here. Just reverse. Now understood, Nandini?
Yes, ma'am.
As we go away from the coil, so field lines will decrease. Correct? So if field lines will decrease, the current induced will be decreased. If current induced will be decreased, then my potential will also decrease. It means EMI decreases, EMF is also decreases. Correct or not?
Yes, ma'am.
Janisha, any doubt, beta?
No, ma'am.
Very good. चल समझा मुझे बेटा. ओ जनिशा. जनिशा, अब ये अनम्यूट ही नहीं करेगी.
Yes, ma'am.
हाँ समझा बेटा. EMF EMI क्या है? बोल बेटा.
Ma'am,
बोलना रानी, जो भी समझ में आया बोल. फिर हिमाक and Nursery. Now it's your turn also. And Nandini, you
to
too.
explain this.
Yes. Acha. Okay, Janisha, I will just, I have already recorded this lecture and I will give it to you in your YouTube. Go through it and then you will understand it very nicely. Okay, Janisha? Imam,
Okay, ma'am.
बोले?
आवाज कट रही है.
आवाज ही कट गई. वाह रे बेटा, सही है. धनश्री, उसकी तो आवाज ही कट गई हिमाक की.
मैं आ गया मैम, आ गया.
अरे सह दे, दूसरे के पास हो गई तो आ गई आवाज. बोल बेटा. धनश्री बोल बेटा.
With the right hand rule.
Whatever. What is EMF? What is EMI? What Faraday said?
EMF is the electromagnetic force, which is basically a potential difference caused when a current is induced. That is electromagnetic induction. Because of electromagnetic induction, when a current is induced, the potential difference that will be experienced is the electromagnetic force, EMF. That was given in his law. And then in this coil arrangement, when a bar magnet is taken, there's no source in this coil. There's only a galvanometer to read the current flow. And when the north pole is brought towards the coil, the current flow is in anti-clockwise direction. That we got from Fleming's right hand rule. And when it's brought closer, there is deflection in galvanometer, and then the current through the coil increases. But when it's taken away, if a magnet is taken away, that is towards the south pole, that time also there's deflection, but then the current decreases.
Now, one thing. Now, suppose my coil is fixed. Now we are pushing the magnet here and there, here and there, here and there, here and there. Obviously, the current is used. Right? Now, third rule. My magnet is fixed. I'm just pushing my coil here and there, here and there, here and there, here and there. Then also the current is induced. Fourth. Coil is also moving with the 4 meter per second. Magnet is also moving with 4 meter per second. Both are moving 4 meter per second. Will current will induced? Will current will induced?
No,
No, ma'am.
No, because both are, someone has to move faster because both are in the same distance, far apart. Someone has to become faster. So if both are 4 meters per second, Okay, then none of the magnet or none of the coil will go closer to each other. So no EMF is produced, no EMI will produce. Understood? So these are the conditions that you have to know. That, write it down in the note. Whenever there is a relative motion, whenever there is a relative motion, see here we have a relative motion between my magnet and the coil, correct? Where we have assigned 4 things, right? That one time I have fixed my coil and magnet is moving. Second, I fixed my magnet, coil is moving. Third, both are moving with the fast pace. Fourth, both are moving in the same space. In the same pace, both are moving. Then that time no current will produce. Correct? Correct now? Nandini? Right. So whenever there is a relative motion between coil and magnet, an EMF is induced in the galvanometer. So an EMF is induced in a coil. If it is a closed circuit, an induced current flows through it. An induced current will flow through it. So, first EMF is induced, then EMI is induced. First EMF is induced, then EMI is induced. Note, write it fast, after that the class will be over. Note, an induced EMF lasts as long as the change in flux is taking place. As long as change in